Hey friend, it's Dastardly Danny. I picked up your distress signal. I see you drifting into deep space, but you're wide awake. Don't worry, I got you.
Hey gang, this is Dastardly Danny. Welcome back. Hey gang, this is Dastardly Danny. Welcome back to Sleep Mode, where I read to you in a soft-spoken voice our spacecraft manual for the Lunar module. We are currently reading the Apollo Operations Handbook, Lunar Module Volume 1, and we're going to continue right where we left off, which is right at this page. So let's continue, shall we? The astronaut uses the TTCA to control throttling of the descent engine and translation maneuvers. The throttle commands, engine on and off commands from the S&C control assemblies. Let me start that over. The astronaut uses the TTCA to control throttling on the descent engine and translation maneuvers. The throttle commands, engine on and off commands from the SNC control assemblies and trim commands from the ATCA are applied to the DECA. The DECA applies the throttle commands to the descent engine, the engine on and off commands to the descent engine latching device, and the trim commands to the GDA. And the SNC control assemblies receive engine on and off commands for the descent and ascent engines from the AEA, as in the primary guidance path. The SNC control assemblies route descent engine on and off commands to the DECA, and apply ascent engine on and off commands directly to the ascent engine. The abort guidance path operates on the automatic mode or the attitude hold mode. In the automatic mode, the navigation and guidance functions are controlled by the AGS, stabilization and control functions by the CES. In the attitude hold mode, the astronaut uses his ACA to control altitude. The ACA generates an altitude rate pulse, direct, and hard-over commands. The altitude rate and pulse commands, the AEA error signals, the rate gyro assembly or the RGA, the rate damping signals, and the TTCA translation commands are applied to the ATCA. The ATCA processes these inputs to generate thrusters on and off commands. In the attitude hold mode, pulse and direct submodes are available for each axis. The pulse submode is an open-loop attitude control mode in which the ACA is used to make small altitude changes in the selected axis. The direct submode is an open-looped altitude control mode in which pairs of thrusters are directly controlled by the ACA. The astronaut can also control vehicle attitude in any axis by moving the ACA to the hard-over positions. In addition, the astronaut can override translation control in the plus axis, negative axis with the plus X transl push button, see panel 5. Pressing the positive X transl button fires all 4 positive X-axis thrusters. Okay, I don't understand that. There's a yaw, a positive yaw, but there's no negative yaw. There's also a positive roll. Okay, several sets of axes are associated with the LM and the GNNCS. Each set is 3-axis right-hand orthogonal coordinate system. Figure 2.2-6 shows the relationship of various sets of axes when the IMU gimbal angles are 0 degrees. The x-axis positive direction is through the overhead hatch. The z-axis positive direction is through the forward hatch. The y-axis perpendicular to the xz plane. The navigation base, or the NB, is mounted to the LM structure so that a coordinate system is formed by its mounting points. The YNB axis is parallel to the vehicle y-axis. The XNB axis is parallel to the vehicle's x-axis. The CNB axis is perpendicular to the XNB-YNB plane and parallel to the vehicle's z-axis. The IMU axes are defined by the three gimbal axes. These axes are defined as outer gimbal axis, or the OGA, middle gimbal axis, or the MGA, and the inner gimbal axis, the IGA. The gimbal axes are defined when the gimbal angles are at 0 degrees. They are as follows. The OGA is parallel to the x-axis, the MGA is parallel to the z-axis, and the IGA is parallel to the y-axis. The axes of the IMU stable member are parallel to the vehicle axis and the gimbal axis when the gimbal angles are at 0 degrees. Inertial reference integrating gyro axes. The inertial references for integrating gyro IRIG axis are designated XG, YG, and CG, are parallel to the LM vehicle axis. If the attitude of the stable member is changed with respect to the inertial space, the gyro senses the change. Where's my cat? Sorry about that. Let's start over. The inertial reference integrating gyro, or the IRIG axis, is designated XG, YG, and CG are parallel to the LM vehicle axis. If the attitude of the stable member is changed with respect to inertial space, the gyro senses to change about its axis and provides an error signal to the stabilization loop of the IMU. The pulse integration pendulous accelerometer, or the PIPA, axis, designated XA, YA, and CA, are parallel to the LM body axis. Velocity changes are measured along the PIPA axis. Okay, below you will see figure 2.2-6. This is the LM vehicle and the GNNCS axis, and it has a breakdown of basically everything that we just spoke about as to where are the designated axis is located in the LM. Yes. And then we have figure 2.2-7, which is the alignment optical telescope axis, which I'm assuming is what we're going to discuss now. The alignment optical telescope, or the AOT, is mounted to the navigation base so that the AOT shaft axis is parallel to the x-axis. The telescope LOS is approximately 45 degrees above the vehicle YZ plane. The AOT LOS is fixed in elevation and movable in azimuth to the 6 detent positions. These detent positions are selected manually by turning the detent selector knob on the AOT. They are located at 60-degree intervals. At 6 positions, which is forward, right, rear, left, and left, are used for the star sightings. The forward, or F, or 0, detent position places the LOS in the XZ plane, looking forward and up as one would look from inside the LM. The right, or R, and right rear, or R, are detent positions place the LOS 60 degrees and 120 degrees respectively, to the right of the XZ plane. Similarly to the left, or L, and the left rear, LR, the temp positions place the LOS at 60 degrees and 120 degrees, respectively, to the left of the XZ plane. The rear, CL, the temp position, places the LOS in the XC plane, looking aft as one would look from inside the LM. In addition to the CL position, 180 degrees from the F position, is the stowage position. Each position maintains the LOS at 45 degrees from the LM positive x-axis. The axes located with the RR antenna are discussed in paragraph 2.2.3.4. The rendezvous radar transporter antenna axis. The axis associated with the RR transporter are discussed in paragraph 2.2.3.5. Landing radar antenna axes. The axes associated with the LR antenna are discussed in paragraph 2.2.3.6. Primary guidance and navigation section will be discussed in figures 2.2-6. Functionally, the PGNS, which is the primary guidance and navigation section, is divided into three major subsections: inertial, optical, and computer. The subsections individually or in combination perform the following functions: establish an inertial reference that is used for measurement and computations, enable IMU alignment through the LGC by entering optical sightings data through the DSKY, enable calculations of LM positions and velocity by inertial techniques, enable LM and CSM rendezvous by radar tracking and inertial techniques, generate attitude control and thrust commands to maintain the vehicle on a satisfactory trajectory, control throttling and gimbal trim on the descent engine, display pertinent flight data related to the guidance status. The inertial subsection, or the ISS, performs the following major functions. It maintains a platform or a stable member fixed with respect to a pre-selected inertial reference frame. It measures the altitude of the stable member with respect to the LM. It senses the LM acceleration due to the thrust along the coordinate system defined by the stable member orientation, and assists in the data conversion for display or telemetry transmission. The optical subsection, or the OSS, performs the following major functions. It provides a mean of aligning the inertial reference on a lunar surface. It provides the measurements for establishing the inertial reference in flight. And computer subsection, CSS, performs the following major functions. It aligns to the IMU. It solves the guidance and navigation problems for all mission phases. It provides control information to the PGNS and other subsystems. Displays pertinent information to the astronauts and MSFN when requested. Provides a mean by which the astronauts can directly communicate with the LGC. And provides on and off controls to the RCS thrusters and the ascent and descent engines. And then here we have the figure, which is 2.2-8, which is the primary guidance and navigation section. This is the block diagram where it will show you the computer subsection and how each subsection basically functions and performs what functions. So let's see what we have here. We have the inertial subsection, which is the pulse torque assembly, power and service assembly, the cooling data unit and inertial channels, as well as the inertial measurement unit. We have the computer section, which is all the LM guidance computer. We also have the display and keyboard, which is minimal, but it is a computer. The optical subsection will have the computer control, the dimmer assembly, alignment optical telescope. That's on its own, and then the computer continues to do programs to the CSS, which is the computer subsection, which I'm sure it aligns to the IMU, coupling data units, and radar channels. Okay, awesome. There's actually more that the computer subsection performs to the following. So the CSS also provides gimbaling and throttling control of the descent engine. It provides the timing for the PGNS and other subsystems. It monitors its own operation and certain other subsystem operations, and positions the RR antenna. Okay. The ISS comprises the navigation base, the NB, the IMU, the coupling data unit, or the CDU, the pulse torque assembly, the PTA, the power and serve assembly, the PSA, and the signal conditioner assembly, which is the SCA. ISS operations can be initiated automatically by the LGC or manually by the astronaut using the DSKY. In order to command the LGC to select various operating modes, the ISS status or mode of operation can be displayed on the DSKY as determined by the computer program. The IMU furnishes the inertial reference, and it consists of stable member with 3 degrees of freedom, stabilized by 3 integrating gyros. The stable members must be aligned with respect to the reference coordinate system each time the ISS is powered up. The stable member must be realigned during the flight because it may deviate from its alignment due to the gyro drift. I also want to apologize, English is not my first language, so I'm not sure if it's gyro or gyro. I know that one of them is an actual delicious wrap with lamb from Greek descendants. But this could be gyro. I'm not sure. Also, the crew may desire a new stable member orientation. The alignment orientation may be that the CSM or that defined by the thrusting programs within the LGC. Signings of the 2 stars is required for in-flight fine alignment. The stable member is aligned after the LGC processes sightings data that may have been combined with the known IMU angles and supplies gyro torquing signals to the IMU. Once the ISS is energized and aligned to the inertial reference, the LM rotation is about gimbaled, stabled member, which remains fixed in space. Resolvers mounted on the gimbal axis act as an angle sensing device and measure LM attitude with respect to the stable member. These angular measurements are displayed to the astronaut by the Flight Director Altitude Indicator, or the FDAI. The angular change of the inertial reference are sent to the LGC. Desired LM altitude is calculated in the LGC and compared with the actual gimbal angles. A difference between the actual and calculated angles result in a generation of altitude error signals by the ISS channels of the CDU, which are sent to the FDIA for display. These error signals are used by the digital autopilot program and the LGC to activate the RCS thrusters for LM altitude correction. Altitude error is displayed by the FDAI error needles. LM acceleration due to thrusting is sensed by 3 PIPAs, which are mounted by the stable member with their input axis orthogonal. The resultant signals velocity changes from the accelerometer loops are supplied into the LGC, which calculates the total LM velocity. The IMU is primary inertial sensing device of the LM. It is 3 degrees of freedom, gyroscopically stabilized device whose primary functions are maintaining an Must have been the wind. Anyways, maintaining an orthogonal inertially referenced coordinate system for the LM attitude control and measurement, maintaining 3 accelerometers in the reference coordinate system for the accurate measurement of velocity changes. The CDU converts angular data and transfers the data between major assemblies of the GNCS. The CDU contains 5 channels for processing these data as follows: 1 for the RR shaft axis, 1 for the RR trunnion axis, 1 for each of the 3 gimbal axes to the IMU. The 2 CDU channels used with the RR provide the interfaces between the antenna and the LGC. The LGC calculates digital antenna position commands before acquisition of the CSM. These signals are converted to analog forms in the CDU and applied to the antenna drive mechanism to aim to the antenna toward the CSM. Tracking angle information is converted to the digital form by the CDU and applied to the LGC. The 3 CDU channels used with the IMU provided interfaces between the IMU and the LGC are between the LGC and the AGS. Each IMU gimbal angle transmitter resolver provides its channel with analog gimbal angle signals that represent the LM altitude. The CDU converts these signals to digital form and applies them to the LGC. The LGC uses these signals to calculate altitude and translation commands and routes the commands through the CES to the proper thrusters. The CDU converts the steering error signals to 800 CPS analog signals and applies them to the FDAI. IMU course and the fine alignment commands generated by the LGC are coupled to the IMU through the CDU. The PTA, or the Pulse Torque Assembly, supplies input to and processes outputs from the inertial components in the IMU. The PTA contains all pulse torquing electronics for the PIPAs and for the IRIGs. The PSA, or the Power and Servo Assembly, contains electronic equipment in the support of the PGNS. Power supplies for generating of internal power required by the PGNS. Servo mechanisms for the IMU, servo loop molding relays, and introverted for the generating IMU temperature out of limits discrete to the GSE. The ISS molding logic uses during the IMU operate turn on. The SCA, or the Signal Conditioner Assembly, receives a PGNS signal and conditions them so that they are acceptable to the IS for telemetering. The CSA also provides isolation between the signal courses, or the signal sources, and the IS. It's a big one. Okay. The inertial subsection and functional loops. These are seven functional loops, 3 stabilization loops, a gyro torquing loop, a 3 accelerometer loop, a 3 stabilization loops maintaining the stable member rotationally fixed with respect to inertial space, and the stable member is used to reference and maintain the orientation of the accelerometers with respect to the inertial frame of reference as the altitude reference for the LM. The gyro torquing loop permits introduction of external driving signals into stabilization loops during closed loop conditions. The 3 accelerometer loops measure the acceleration of the stable meter along with 3 orthogonal axes and integrate these data to determine velocity. The LGC uses the velocity data to compute LM trajectory. The accelerometer loops also generate torquing signals for torquing the PIPAs back to a null position after sensing an acceleration. Stabilization loops. See figure 2.2-10. When stabilization loops hold the stable member inertially referenced, any movement of the stable member is sensed by one or more of the 3 IRIGs. This results in an IRIG signal generator, 3200 CPS error signal output, which is proportionally to the rotation of the gyro, which is input axis. This error signal is then amplified by the preamplifier, which is an integral part of the IRG assembly. The Y gyro error signal passes directly to the associated gimbal servo amplifier through the normally closed contacts of the course alignment relay. The X and C gyro error signals are resolved about the IGAs by the gyro error resolver before being introduced to the associated gimbal servo amplifiers. The servo amplifiers' current output is fed to the appropriate gimbal torque motor to restore the stable member to its original reference position. Do you guys hear that? Suspicious. Anyways, where was I? As stable member is returned to the original disturbance input, the result is precession of float. Due to the precession, the float returns to its null position. Because no signal generator output is then present, the loop is nullified, and no further drive signals are applied until another disturbance is introduced. I'm hearing stuff. Okay. Resolution of the X and Z gyro error signals is required because motion about the MGA or the OGA with the stable member at some angle other than 0 degrees is sensed by the X gyro and C gyro. The resolver then sums the components of gyro error and lie along the MGA or OGA and directs the gyro errors to the applicable gimbal servo amplifiers. When the stabilization loops are inertially energized, the stable member is referenced to the LM axis by driving the gimbals with an error signal inserted at the course alignment input to the gimbal servo amplifiers. Course alignment relay energized. If a specified inertial reference is desired, the stable member is aligned to the desired orientation. Using the stabilization loops, the alignment is accomplished in 2 steps: course alignment modding and fine alignment modding. During this course alignment, the gyro error signals are disconnected from the gimbal servo amplifiers. Instead, 800 CPS error signals are injected through the course alignment relay to torque the gimbals to approximately the desired position. For fine alignment of the stable member, the course alignment relay is de-energized and gyro error signals are injected in the loops for additional gimbal torquing. The gyro error signals are generated by torquing the IRGs with pulses originating at the LGC and processed through the pulse torque or fine alignment electronics loop. The stable member is when aligned and the stabilization loops holding in its final position. Gyro torquing loop, see figure 2.2-10, using a torque generated to torque the IRG floats, it is possible to drive the IMU gimbals to a new position. This permits fine alignment to the stable member to a desired reference with considerable accuracy. When gyro torquing is required during the fine alignment mode of operation, the LGC issues pulses, which are controlled by the program 52, that 1. Enable torquing electronics, 2. Select gyro to be torqued, 3. Select direction of torquing, and 4. Control the amount of torque applied. The 3 RIGs are sequentially torqued by the LGC during the fine alignment. It is possible for all 3 gyros to be controlled through one set of torquing electronics. While torquing electronics consist of a gyro calibration module, a binary current switch, and an ADC differential amplifier, and precision voltage reference module, and a pulse torque power supply module. Basically, the gyro torquing loop operates by applying a constant current to the torque winding in the IRIG. When torque pulses and gyro-select pulses are initiated by the LGC, a constant direct current is applied to the IRIG, and the float is torqued in a specific amount. A specific amount in the IMU gimbal rotation is provided. The number of torque or set pulses applied to the current switch determines how long torque. The number of torque set pulses applied to the current switch determine how long the torquing current is applied. The gyro-select pulses enable switching network in the gyro calibration model, which closes out a current path through specific winding and specific gyro positive or negative torquing of the float. Before and after torquing, the LGC issues a North torque reset pulses to the current switch, which enables constant current to flow along the dummy path external to the IRIGs. This reduces transient when torquing is initiated. The torquing loop is enabled by the LGC command, which energizes a relay to applying power to the loop. The constant current supply consists of the DC differential amplifiers, the pulse torque power supply, and the current regulator in the binary current switch. The 3 accelerometer loops are identical. The pulse torque power supply provides a positive 20 and a negative 20 and a positive 120 volts DC. The 3 accelerometer loops are identical. The pulse torque power supply provides a positive 20, negative 20, and a positive 120 volts DC, and a positive 28 volts DC regulated to all the loops. The PIPA signal generator outputs are two 3200 CPS error signals, which are the opposite phase of the proportional to the rotation of the pendulum about its output axis. These error signals are amplified by the preamplifier and then routed to the AC differential amplifier. There, the 2 signals are summed, the resultant is amplified, and then phase split. The 2 resultant signals are the opposite phase. They are fed to the interrogator circuitry, which determines the direction of pendulum movement and generate positive or negative commands, indicative of the direction movement. The interrogator and switching pulses from the LGC are used to generate the positive or negative torque pulses from the binary current switch. The binary current switch uses the interrogator outputs to generate torquing current to torque the pendulum back to pull, and pulses that represent velocity changes. The velocity pulses are generated by providing data pulses from the LGC, such that the velocity outputs are positive or negative increments of the velocity. The torquing current is generated in a manner similar to that what is used in the gyro torquing loop. The constant current supply consists of an ADC differential amplifier and precision voltage referenced a current regulator. Constant current is supplied to the binary current switch. A positive or negative input commands turn onto a positive or negative current switch, routing a positive or negative torque signal to the torque winding in the PIPA. The torquing current The torquing current is fed to the PIPA's torque generator through a load balancing network in the calibration module. This ensures that for a given amount of torquing current, an equal amount of torque is developed in the positive or negative direction. When the accelerometer loops operate, a certain amount of the PIPA's torquing occurs at all times, even during periods of no acceleration. This torquing continuously moves the pendulum an equal amount in the positive and negative directions. As a result, an equal amount of positive and negative velocity pulses are sent to the LGC. When an acceleration is sensed, more of one type of pulse is generated. This unbalance produces either positive or negative AV pulses, which are routed to the LGC PIPA counter to be accumulated as LM velocity changes. The inertial subsection modes of operation, see figure 2.2-11. Except for the IMU cage, the inertial reference modes, the modes that are controlled by the CDU, are commanded by the LGC. The IMU cage mode is initiated with the IMU cage switch or panel 1 is set to on. The inertial reference mode is entered automatically whenever the ISS is not in another mode. The CDU logic receives from the LGC the following discrete commands: the ISS CDU 0, the ISS error counter enable, the course align enable, the RR CDU 0, the RR error counter enable, and the display inertial data or the DID. Alright gang, that's all for tonight's readings. You made it through another section of the manual and hopefully into a peaceful orbit of dream. Sleep well, and I'll see you on the next mission. And if you need me or you need more, just click on the next video. See you next time. Bye.